The catastrophic outage of the payment network paralyzed transactions for hours, costing businesses millions and eroding customer trust. This event underscored a critical truth: no system is inherently immune to failure. The objective is not to prevent every individual component failure, but to design an architecture that maintains operation, data integrity, and rapid recovery when failures inevitably occur. Traditional approaches often focus on maximizing uptime through redundant components. While necessary, mirroring a single server or database only shifts the failure domain. A more robust strategy demands a holistic reevaluation of how systems respond to adverse conditions across all layers. True resilience begins with distributed architectures. Decomposing monolithic applications into independent services, often microservices, isolates failure points. A problem in one service does not inherently cascade to others, provided appropriate boundaries and communication protocols are established. Data integrity and availability are paramount. Replicated data strategies range from active-passive configurations, where a primary serves requests and a secondary stands by, to active-active setups that distribute requests across multiple replicas simultaneously. Each presents trade-offs between consistency, availability, and network latency. Synchronous replication ensures strong consistency by committing writes to all replicas before acknowledging success. This guarantees no data loss but introduces latency. Asynchronous replication offers lower latency but accepts a window of potential data loss during a primary failure. The choice depends on specific recovery point objective requirements. Fault isolation is critical. Implementing bulkhead patterns, analogous to ship compartments, prevents a failure in one section from sinking the entire system. This means dedicating resource pools, such as thread pools or connection pools, to specific downstream services, limiting the blast radius of an unresponsive dependency. Circuit breakers prevent repeated attempts to access a failing service. After detecting consecutive failures, the circuit trips, redirecting requests away from the unhealthy component for a set period. This allows the failing service to recover without additional load, preventing cascading failures. Rate limiters protect systems from overload. By controlling the number of requests a service processes within a given time frame, they prevent resource exhaustion and maintain stability, even under unexpected traffic spikes or denial of service attempts. Graceful degradation ensures critical functionality remains available even when non-essential components fail. For instance, an e-commerce site might disable product recommendations during a database issue but continue processing orders. This prioritization maintains core business operations. Automated failover mechanisms are essential. Manual intervention during an outage introduces delays and human error. Orchestration tools detect failures and automatically redirect traffic to healthy replicas or alternative data centers, minimizing downtime. Immutable infrastructure reinforces resilience. Instead of patching or updating existing servers, new, fully configured instances are deployed, and old ones are decommissioned. This reduces configuration drift and ensures consistency across environments, simplifying recovery and preventing snowflake servers. Observability is the bedrock of resilient systems. Comprehensive monitoring, logging, and tracing provide deep insights into system behavior, enabling rapid detection, diagnosis, and resolution of issues. Without clear visibility, failures remain opaque. Chaos engineering proactively tests resilience by injecting controlled failures into production environments. By simulating network latency, server crashes, or resource exhaustion, teams identify weaknesses before they cause real outages, building confidence in system robustness. Distributed consensus algorithms, like Raft or Paxos, maintain data consistency across multiple nodes, even in the presence of network partitions or node failures. They ensure that all healthy nodes agree on a single state, critical for highly available data stores. Disaster recovery planning extends beyond component failures to regional outages. This involves geographically distributed deployments, regular backups, and tested recovery procedures to restore services from catastrophic events within defined recovery time objectives. Data backup and restoration strategies must be rigorous. Beyond local replication, offsite backups and point-in-time recovery capabilities are crucial. These ensure that data can be restored to a consistent state, even if primary and replicated data stores are compromised. Security vulnerabilities represent another class of system failure. A compromised system can lead to data breaches, service disruption, or complete operational shutdown. Integrating security practices, such as least privilege access and regular vulnerability scanning, is integral to resilience. Ultimately, building unbreakable resilience is an ongoing process of continuous improvement. It requires a culture that embraces failure as a learning opportunity, leveraging postmortems to refine architectures, processes, and automation, thereby evolving towards truly robust and continuously operational systems.